introduction, and thanks for coming. So my name is Chan Park. I'm a postdoc at Rutgers University studying string theory. And today I want to share with you my experience of using Python in a recent research project. And as a teaser, let me start with showing you the end product of the project called Loom, which can be found at this location. And if you go to the location, you can see this web page, which contains many colorful diagrams, colorful plots generated using the Python program for real string theory research. And also you can go to a configuration page, and you can, insert a few parameters, and then, for example, you can click a button to generate a colorful plot, which will take a couple of minutes. So instead of waiting for it to be finished, like our Food Network show, let me show you a prepared plot, which is like this. So here is a colorful plot where you can, you can interact with it, like dragging, zooming in, and like seeing some labels on it, like this. And you can change the plot by sliding the slider bar. And well, on the lower left part of the slide, you can see a URL. If you visit this web page, you can see the link for this slide, as well as the link for the Python web program itself, and also many examples of colorful plots. So, well, if you find too bored during my talk, you can visit the website and enjoy yourself with many colorful plots. And I'll just do my best so that my small server will not break down from too many requests from this room. So, so let's start today's talk. So here is the outline of today's talk, and well, half of it, a little bit more than half of it, will be about string theory, and half of it will be about how I built the program that I just introduced to you with Python. So let's start with before going into the main part of the talk, the goal of today's talk will be to illustrate how Python is integrated throughout the progress of this project, so that Python programmers and developers who want to know how a math-oriented theoretical physicists use Python, and also scientists who are interested in using Python but have difficulty in figuring out where and how to start, can use this as a case study of a collaborative research project using Python. So a brief introduction to string theory. So what is string theory? Well, first of all, theoretical high-energy physics, more commonly known as theoretical particle physics, is a study to understand fundamental forces of nature. And you may heard of the Fantastic Four: the electromagnetic force, weak force, strong force, and gravity. And this theoretical high-energy physics includes string theory, which started as a candidate theory for quantum gravity, and now it's evolved into an effort to build a physical and mathematical framework to describe the fundamental forces in a unified way. So the questions in string theory are, well, in nature mathematical, and why do we care about computational analysis? Well, we do indeed like to have a mathematical and exact answer, but many problems are too difficult to find such a beautiful answer, and we often find ourselves quite confused, like the poor kitty in the picture. So in that case, we can tackle such a problem by using a computational method, and this can be a great hint toward formulating a complete and exact answer. So that's why we use computational method, and let me introduce a few concepts in string theory that will appear throughout the talk. The first thing is M-theory. So M-theory is a prospective theory of quantum gravity that lives in an 11-dimensional space-time, meaning 10-dimensional space and one time direction. And this is called M-theory partly because this is believed to be the mother of all string theories, because different string theories are believed to be different limits of this theory. And this M theory contains two extended objects called M2 branes and M5 branes. M2 brane on M2 brane spans two spatial direction and one time direction, so hence the name M2. And M5 brane spans five spatial directions and one time direction. And these objects satisfy a mathematical relation between their masses m and a quantity z called a central charge, which can be considered as an analog of higher dimensional analog of electric and magnetic charge. So what do we do with these M branes? First, we can start with an M5 brane. We wrap this six-dimensional object onto a two-dimensional surface, more precisely a Riemann surface with punctures, and then through a high-level math of 6 minus 2 equals 4, we obtain a four-dimensional supersymmetric gauge theory, which can be considered as a mathematical model of real-world particle physics. One interesting thing is this two-dimensional thing, the geometry of the two-dimensional surface, will determine the physics of the four-dimensional theory. So this is one example of interplay between geometry and physics in string theory. So we use M5 brane to construct a theory. Then what about M2 branes? Well, an M2 brane whose boundary ends along the two-dimensional surface can give us a supersymmetric particle in the 4D theory. And its mass is given by an integral along the boundary on the two-dimensional surface. So this is how we obtain a theory and particle contents of the theory using extended objects of M theory. And physics is determined by the geometry. So it becomes a geometric problem. Then the boundary of such an M2 brane satisfies this differential equation. And we can actually turn this question around, and we first can look for solutions of this differential equation, which will be geometric flows on the two-dimensional surface. And actually, those flows are the colorful lines that you just saw in the demonstration of the program. So we can collect all the solutions, and we can look for a particular configuration that will correspond to a boundary of an M2 brane, which will give us a particle. So this kind of technique, this kind of tool is called a spectral network because we can find particles and therefore a spectrum of the given theory. So well, what it can do with a spectral network, we can do a supersymmetric spectroscopy. And for that, let me remind ourselves what we have learned in a high school science class, a flame test, which is a qualitative method to identify an atomic element in a chemical compound by putting the chemical compound into a torch, for example. And actually, we can do better. We can use a diffraction grating at the light of the flame to obtain an emission spectrum, which can be used to distinguish atomic elements in a quantitative way. And well, the idea is kind of similar in a supersymmetric spectroscopy. We start with a diagram called spectral network, and by evolving this network, we obtain particular configurations which will correspond to the particles, and this will give us a spectrum of a given theory, and using the spectrum, we can identify what the theory is. So in practice, what we do is we generate a family of plots like this, and we look for a moment where something happens like this, and this is exactly the moment where we have a supersymmetric particle appearing in the theory, and we can collect such a moment, and we can analyze the plot itself to figure out the information about the supersymmetric particle, and then construct a spectrum. Then we can use that to identify a theory. So this is the string theory part of the problem. And let's turn this physics problem into an explicit computational task. So I said that we start with a punctured Riemann surface, a two-dimensional surface, and this is described by this equation with two variables x and z, and we wrap this Riemann surface onto a z-plane as a multi-sheeted cover. Then this equation will give us the locations of the branch points and branch cuts. So that's the start. And from each branch point, we can find the solution of the previous differential equation. And we do that for the other branch point as well. Then there can be an intersection between two different curves. And when they satisfy a certain mathematical relation, more precisely, if the roots of the two curves sum up to another root of the Lie algebra associated with the theory, if that condition is satisfied, then there can be the third curve coming out of the intersection. And we repeat this procedure until we get the full network at a fixed value of theta, and this plot, this network, is called a spectral network. And then we can repeat the procedure for different values of theta, where this theta is the parameter of the differential equation we saw before. So we obtain such a solution for various values of theta. Then we can obtain a family of spectral networks like this. And again, as I told you before, we look for a specific moment where something happens like this. And actually, when this happens, this two-way street between two branch points corresponds to a boundary of an M2 brane, which looks like a disk. And this corresponds to the moment where we have a supersymmetric particle. So this is our computational task. That is, we start from the equation of the Riemann surface, and we want to find this network out of that equation. So that is the physics part of it. Thank you for bearing with me through this mathy and physics talk. So now we can start talking about the program part of this. So, well, previously, before Loom, there were several mathematical codes for generating spectral networks. Well, partly because, Mathematica is still the most favorite math package for string theories because of this, because of Mathematica's very user-friendliness in manipulating symbolic mathematics. But, well, Mathematica is not the great tool in developing a program in a collaborative way. So by we I mean some string theorists working on these spectral networks, we maintained, each of us maintained separate mathematical codes, and of course this is an overlapping mismatch of time and effort. And well, Mathematica is a commercial program, so there's the issue with the number of licenses available. And well, the numerical accuracy is not that great. And also, well, its internal warnings and errors were quite hard to understand. So I launched an open source project Loom on GitHub and started a collaboration with my friend string theorists, working on spectral networks in the hope of converging our effort together into building one program and share that among each other. And well, why I chose Python to write this program? Well, first of all, my physicist colleagues don't have much programming experience, but Python is easy enough for them to learn how to work with it. But on the other hand, Python is a full-fledged standard programming language. So that's the first thing and the first reason that I chose Python. And of course, all the libraries that I needed and used are open source, and it means that I can look into what's going on in the box if I want, and I don't have to second guess an incomprehensible error message. And of course, active and helpful Python community is a big plus. And powerful libraries in SciPy stack they are just great. And also, Python is quite easy to work with external libraries, which I will tell you a bit more in just a moment. So I started writing a Python program. So let me guide you through the construction of Python program Loom. And let me start with the core part of it. And if you remember the description of the computational task that I told you, we start with an equation for the Riemann surface, and we need to massage that equation into a differential equation. And for that task, we definitely need SciPy. But sometimes this equation for the Riemann surface can be a bit complicated, and in that case, SciPy has been quite useful, and also SciPy's extensive knowledge over Lie algebras and their representations has been very crucial in studying spectral networks. But SciPy itself is not a Python library, so it has to be called by loom using Python's subprocess module. And then after we have this differential equation, we need to solve it to find those geometric flows on the Riemann surface, on the two-dimensional surface, and definitely we use SciPy and NumPy, and especially NumPy's ND array is implemented using contiguous memory model, and thanks to that, it was very useful in storing data and exchange it with a external C++ libraries that I'll tell you in a moment. But also, thanks to that, the operation on NumPy objects for NumPy array was very fast. And if you remember the computational task, after we find those curves on the Riemann surface, on the two-dimensional surface, we need to find intersections between two curves. And for that, I used a C++ library called computational geometry algorithm library, which can be found at this address. And this is a C++ library, so you need to glue this into Python, but I mean, Python was just great in gluing such an external library, so relatively little pain in doing that. And then this, generating a family of spectral networks for different values of theta is naturally a collection of parallel jobs that can be managed as a pool of worker processes. And this was also quite easy using Python's multiprocessing module. And because generating networks is the core part of the program, and this was done in parallel way, it was possible to boost the throughput of Loom linearly with the number of available CPUs. For example, in our group, we have a 40-core workstation, and Loom is happily dwelling on that machine, chugging out many plots. But because we are doing this in a parallel way, there is, of course, an overhead of inter-process communication. And also, the core part of Loom itself is separated from the front end, which implements user interface. So there is also two different processes involved. So, well, usually inter-process communication between different processes is quite a work, and I was a bit worried about the amount of work. But fortunately, Python's logging and multiprocessing.q made the whole process really easy, and it was quite a small amount of work to, for example, make data to be exchanged using this multiprocessing queue. And lastly, for the core part of Loom, we need to save and load data efficiently, because it takes like a couple of hours to generate a real data for research. And for example, I cannot ask my colleague to run it every time when we need to investigate a theory. So it was very important. So there are two parts of data. First one is the configuration, containing the information regarding the theory and the numerical setup of the running. And this was done using Python module config parser. And there is this generated data large part of it. And I chose JSON mainly because of the portability across platforms, because my collaboration includes like Mac users, Windows users, Linux users. So portability was very important. And well, Python support for JSON was great, so it was very easy to save and load data into a JSON format. And well, it was unexpectedly fast actually, considering the JSON data format is natively just a text file. But because of the format, the size of JSON data can be quite large, but we can use zip file module to create a compressed file on memory, and this makes transferring such a data over the internet less burdensome. So this is the core part of the loom. And then there is the front-end part of the loom, and of course the most important part of it is visualizing data. And we use Bokeh and Matplotlib at the same time. Bokeh is used to make a plot as a self-contained dynamic HTML plot, so I can exchange a result with my colleagues with ease. And well, also it is very useful in interactively investigating data like this. And on the other hand, Matplotlib is very useful when debugging and analyzing data, thanks to its full control over visualizing data, and also when drawing plots in vector graphics for research paper. And then when running Loom on a local machine, it is quite useful to have a GUI, so one is implemented using tkinter, but actually more emphasis was put on developing a web application and web user interface, because, well, my friends theorists found it a bit difficult to installing Python and installing Loom and required libraries. So instead of telling them how to do so, I just built a WSGI application based on Flask that can be run on an Apache web server, and this web application itself manages multiple instances of Loom processes. And the web user interface itself is implemented using JavaScript and callbacks for Bokeh, which themselves are JavaScript, and also using server-sent events for receiving message from Loom and sending it to the client web browser. So here is again another look at the front end of Loom, which is implemented using plain HTML, Flask, JavaScript, and so on. So if if I show you again how it works, these messages are coming from the core part to the front end via the server-sent events. This is a one-way. Server-sent events is very easy to use when sending message one way. If you need a bidirectional message communication, WebSocket would be better. But anyway, so that's the whirlwind tour of Loom. So let me conclude my talk. So, this program resulted in one research paper, which is now under revision for the peer review journal, and also 2 or 3 more papers are on the line. So I can at least say that Python has provided a wonderful suite of libraries that were quite useful to theoretical physicists like me. Mathematica is still the #1 most popular math package among theoretical physicists, but we do hope to have an open source alternative. And I see a great potential in Python, SciPy, SageMath, and Jupyter. And let me lastly thank to my friends Pietro and Andy, whose contributions have been crucial throughout the progress of this project. So, source code of Loom can be found here. This is the link to the physics paper. And there is more hardcore physics slide, which you can find at this location, and you can just scan this to access this web page, which shows you slides, examples, and so on. So yeah, thank you very much.
So are there any tools for people that are trying to transition from Mathematica to Python?
Yes, the question is if there is a tool for people who want to, to turn a Mathematica code to Python code. Actually, no. So that would be really great to have one. But well, turning the Mathematica code itself to Python, it may be a long shot. But at least what you can expect is to turn a small bit of mathematical expression to like SciPy expression, and actually that would greatly help us because although like translating a very complicated mathematical formula by hand is very error prone. But yeah, so I asked the question to the SciPy developer who presented a great talk today, and it seems that it's on their priority and is on the progress. But yeah, as far as I know, it is not yet on the scene, unfortunately. But yeah, we do hope that something like that will happen. Or maybe, we physicists can contribute to the effort so that we can be a part of the effort from moving toward the, moving toward the open source community. So, yep.
Looks like this was very useful for exploring the data and understanding the properties of the spectral system that you have. Do you anticipate it's going to be helpful in getting attention to your publication, kind of these interactive plots?
Oh yeah, that's another good question. So in our field, we usually publish a static PDF on this website called Archive. That's our usual procedure. And unfortunately, Archive itself doesn't support any dynamic content on on the for the papers that are uploaded on their website. First, they know about it, and actually day by day, the organizers of the archive, they also want to have some dynamic contents on the paper that are uploaded. That's one thing. But for now, so what we ended up doing was we just provided links to various plots, and that's why we wanted to use Boki, because using Boki we can create a static HTML plot for each of the spectral networks. And for example, if someone wants to study it carefully, then the person can just download one HTML plot and go through it on a local laptop or desktop, so on. So you don't have to generate all the time the data, which takes like a couple of hours, which is kind of pain. So yeah, that's why we were able to also upload those example plots on the web page. And actually those are the plots that we cited in the paper. So that's how we communicated with our colleagues. But indeed, it would be more exciting if we can publish such an interactive data on the paper itself. But I don't know if that's being done in other fields. It may be interesting to hear about it, but yeah.
You mentioned Jupyter. But so how do you see it changing to use?
Oh yeah, right. So one thing that theoretical physicists like about Mathematica is their notebook environment. And on the notebook environment, it's quite easy to manipulate some complicated mathematical expressions. So if we want to do a similar job on a console, for example, it would be a bit challenging. But for example, if we use Jupyter, that's more or less quite similar to the experience of using Mathematica notebook. And well, Sage Math also has its notebook environment, and it's I don't know. It can be better if the two environment can merge into a single best option. On the other hand, it may be not a bad idea to have two horses in the race. But anyway, so that kind of environment is quite crucial, I think, for the transition from using Mathematica to using SciPy or SageMath. So that's why I think Jupyter is quite crucial in that transition. And indeed, I mean, it seems that it's quite close. I mean, we are quite almost there in some sense, but it would be better if it can be a bit, it can be improved a bit more, so that physicists who are not experienced programmers can also use this Jupyter environment as easy as they are using Mathematica notebook, for example. Yep.